Okay, everyone, let's get started. So today my goal is to review the RISC-V assembly language and then show you how to use RARS, which is the simulator we use for class, and then assign the first lab, okay, which will be due on September 8th. So it's a short programming project, okay? So as I mentioned last lecture, Monday, we're using the RISC-V instruction set. It's very similar to MIPS that you learned in 212. It has 32 general purpose, meaning integer registers that are numerated 0 to 31. Register 0 is always read as 0. They also have these alternative kind of symbolic representations too. So there's S0 through S11. You might remember using that register notation in 212. The reason that they're called S0 to 11 is by convention, the values in there are supposed to be saved across subroutine calls. So if you call a function and after it returns, you should have the same values in there that you had prior to calling the function. Of course, that's only implemented in software. There's no hardware support for that. So it's just a convention. And then you've got temporary values, T0 through T6, that are not by convention preserved across function calls. So these S registers are usually used for like sub-expressions, or I'm sorry, actually, the S would be like a loop counter, something like that would be alive a little bit longer, whereas the T's would be like a sub-expression, value, intermediate value that doesn't have to be maintained in the register file as long. And then we have these A0 through A7, which are function arguments. They're supposed to be used for function arguments, and we're going to be, those are also used for system calls, which we'll talk about today. And then there's a return address, stack pointer, global pointer, temporary pointer. We're not using the stack or we're not using the stack in this class. In fact, we're not using any of these pointers because we're not actually going to implement loads and stores on our CPU. We will do a little bit of that in the first lab. And then the RA is the return address for when you use a jump and link by convention, which is register 1 in RISC-V and register 31 in MIPS. You guys remember the return address? Did you use that, like a jump and link? And then the 0 is the same as the 0 register. So when you write your assembly code, you can choose whether you want to refer to the registers as their number, which would be X0 through X31, or if you want to use these names for registers. That's up to you. I kind of flip-flop back and forth, right? So I mentioned last time that one of the issues with this writing code in assembly is that you have to keep track of what's in each register. That's probably the hardest problem. And you have to choose how you want to allocate the registers, which numbers you want to assign to each variable, right? And then you have to keep track of that and keep track of how long that register is alive in your code so you don't overwrite it too early or recycle it too early, right? And also, the instructions only operate on up to 2 registers as inputs. In other words, the machine can only add, subtract, multiply, or divide 2 values at a time. And so if you want to perform more complex arithmetic, you have to assign registers to hold intermediate values, right? Sub-expression values. And then there's also immediate instructions, which is where instead of the second operand, you have an immediate value, which is like a constant, right? You guys all remember that? I'm going through this real fast because I'm assuming you covered all this in 212. I just want to refresh your memory because it's probably been a couple of years since you took it. Okay, so here's an example where I start out with a line of C code. And then the idea is to lower this down into assembly code, convert it to assembly code. So sometimes it's helpful when you're writing the assembly code to actually put a line of C code in there in a comment, and then under there you can have the corresponding instructions that perform that. So in this case, I'm adding G and H, and then adding I and J, and these 2 sums are being assigned to T registers, temporary registers. And then I subtract the sub-expression, right, to get the final result. The problem is that these variables, the input variables, which is G, H, I, and J, and they have to be loaded, right, into registers first. So I've got load word instructions there to load each of those into registers S1 through S4. And then once I calculate the output F, which is being put into S0 here, then I store S0 to F. Does that make sense? Here's another example where I have just a mathematical expression being assigned to a variable. And in this case, I have this temporary variable T0, which holds the product of B plus C and D, right? Because let's see, B plus C. So B and C are in T0 and T1. They're added here. The result is put into T2. The output register is the one listed first here. And then the B plus C sub-expression is then multiplied by D, which is loaded into T3. So T2 times T3 is put into T0. And then I have to add that to B, which I have previously loaded into T0, and then I store that result back to A. Right? You guys all remember that? Everyone comfortable with that? Okay. So normally a compiler does this, but in this class, actually, you could use a compiler. We've had instances in the past where students were so opposed to writing assembly that they just used a compiler to generate it, and that's up to you. I haven't had anyone do that for RISC-V yet, but you could just use a compiler if you wanted to generate this. Yes?
You didn't wipe out when we did that multiply?
Yeah, you're right, actually. Yeah, B would be overwritten here with the multiply, and then it would have been, yeah, that's a good point. That's a bug. Yeah, thank you.
I think you meant T4, it looks like over there.
Yeah, I think what happened was, actually, I know what happened. I think I know what happened. The reason why T0 is red was because originally this slide was meant to highlight this bug where, yeah, because see what happened was I wanted to recycle T0, but I recycled it too early because that B was still alive in there at the time. Yeah, that was the problem. I forgot. Yeah, I changed my slides a little bit and I repurposed this. This used to be under the heading of why it's annoying to have to manually allocate and keep track of registers. Yeah, so anyway, yeah, that's a good point, but that's why that's red. Just wondering. Okay, and by the way, that's a very common type of bug that you'll see in code, assembly code. Okay, so I mentioned that when you do an if statement in assembly, it's a little awkward as compared to the way that you would do it in a high-level language. So in a high-level language, you have, in an if then else, you have a condition for the if, right? And if that condition is true, you execute the code just below that condition, right? And then if the condition was false, you go to the else block. So what's happening here is that if this condition is false, you're jumping down to the else part, right? The else part is lower than the then part, right? The then part comes first, the else part comes second. The problem is that in assembly, when you do this comparison, what's happening there is that you're branching if the comparison is true. So if the comparison is true, you're going somewhere else, right? So you have to decide how you want to handle that. One way to do it is to take this condition and logically complement it. So instead of checking to see if A is less than B, you instead check to see if A, which is S1 in this case, established through this load, is greater than or equal to B, which is an S2, right? Which is just the opposite. It's like saying if A is not less than B, if A is not less than B, then it must be greater than or equal to B. So the condition is greater than or equal based on this mnemonic here, right? And the reason I did that was because if the complement of this is true, then I want to go down to the else part, which is lower, right? So, and then that way I can put the then part in what's called the fall through part. The fall through is if the branch is not taken, that's the part immediately under when the condition is tested. is equivalent to the then part in the high level code, right? So this is kind of an annoyance for assembly because you have to, you have to deal with that. Now there's other ways to do this. You could just simply you could make this branch if less than, and then have this be the then part, right? The then block could be at the branch target, right? Just fine, except in that case, your then is on the bottom and your else is on the top, and that's kind of confusing because that's not how you write code, right? Another option would be you could have a branch to test to see if A is less than B, which if it is, you would jump over an unconditional jump that would bring you to the else part, right? But then that requires adding additional instructions, right? And introduces the more potential for bugs. So this is the way I typically do it. And then for an if loop, normally when you write a loop in C or Java, you use a for loop or a while loop, both of which are pre-test loops, meaning that the condition for executing another iteration of the loop is tested before executing the first iteration of the loop, right? So you kind of have a similar problem here where you have to initialize this loop iterator, and then you have to check to see if you want to continue with the loop, right? And then if you don't, you have to, jump out, go away and exit the loop. A lot of times, though, in assembly language, if you're writing a loop like this, where it's going to iterate at least once, right? Because you're initializing I to 0 and you're going to do 100 iterations, then you might as well structure it as a post-test loop, meaning that you basically simplify it and you can assume that the loop will execute once. So you can put the condition for continuing the loop at the bottom of the loop body to determine if you're going to take the next iteration. So what I'm saying is that this is technically correct. Well, no, it's actually technically incorrect because it doesn't match the semantics of a for loop, which is a pretest. But because these loop bounds are fixed, right, you're safe to write it as a post-test loop, right? So when you go into this assembly code, you're not checking the condition before the first iteration, right? That's the difference. Does that make sense? So this is often more convenient to write it like this in cases like this where you don't care about it being a pre-test loop. You guys with me? But again, you can write this as a pre-test loop if you want. It's just going to take an extra instruction. Okay, and then I mentioned too last time briefly that one of the huge annoyances in RISC-V and in MIPS is that there's no index register, so you have to calculate effective addresses for accessing memory. Now luckily in this class, we're not going to be doing a lot of that because the hardware design in this class where we design the processor is not going to include load and stores. So you don't have to worry about that too much. But I had this on here just to illustrate one of the reasons why writing RISC assembly is so painful, because you have to, in this case, you have to keep track of this loop counter, right? But then in order to use that loop counter as an index into these two arrays, you have to maintain these arrays separately, and you have to calculate effective addresses by taking that I and multiplying it by the size of the element in the array, right? So it requires a lot of extra instructions, which would be a lot simplified if there was a way to do indexing inside of an instruction, like just have a register that serves as the index, but you can't do that. The only thing you've got with load and stores are this base register, which is just a pointer that's dereferenced, right? So you have to calculate that pointer before you access the arrays, right? Yes?
So the LA is load address, so it's
Yes.
loading the address of that DST label into that register.
Yes, yeah, that's a good point. The load address is a pseudo instruction. There's no hardware instruction for that. That actually gets converted into a sequence of instructions that just loads constant values into there based on the symbol table. There's a symbol table in the assembler that keeps track of the address of these variables, right? So in your assembly code, you're going to be using variable names. The assembler will keep track of what address those variables are at in a table, and then it will substitute the addresses in the actual code as constants, right? So the addresses will be constants in the code. That's the machine code. I think I have an example of that. Yeah, so here's an example of that here, actually. So this load word var into x2 is translated into 3 instructions. The first one is an AUIPC instruction, which is actually a hardware instruction that takes the program counter, it takes the upper bits of the program counter, and it substitutes in the lower 20 bits from the instruction, which always seems silly to me because the program counter is pointing to your code, right? And you're using that to form an address that will be for data. And usually code and data are in vastly different parts of the memory. So it's kind of strange that RISC-V does the addressing that way. That's not how MIPS did it. MIPS used a load upper immediate followed by an OR-I instruction to load an address into a register. RISC-V does this weird thing with this AUIPC. And I don't know if that's just, maybe it's not all RISC-V assemblers, maybe it's just RARS that's doing that. But yeah, you'll see that in your machine code, that AUIPC. That's not one that we're going to implement. Although we're implementing one very similar to that with the jump and link, which also puts the program counter into a register. Okay, so I'll skip past those for now. So the goal by the end of the semester, I'm just going to give you kind of the final project in the course, is we're going to implement a minimal set of RISC-V instructions in hardware that's actually complete enough that if you did have a GCC compiler that compiled into RISC-V, chances are all the instructions you get from that compiler will be ones you have in your CPU. There's a fairly small chance that it'll generate one you don't have. In other words, you're going to be implementing the most commonly used instructions in RISC-V. The only exceptions there are the loads and stores. So we're going to implement these R-type arithmetic, logical, and shift and comparison instructions. So these are all very similar. You might remember from 212 that really the only difference between these instructions in the hardware is what you tell the ALU to do. All the other data path operations are the same with all these. In other words, you load the contents of 2 input registers, you route them into the ALU, you tell the ALU to do something which is determined by which instruction is being executed, and then you take the result of that and you put it back in the register file. So pretty much all these instructions are identical, so you're going to be doing a lot of copying and pasting inside your control unit. The only difference is that what the ALU does is different, right? And so we'll be implementing all those. Then we have some here that are a little unusual. So there's 3 multiply instructions. The reason for this is because when you multiply 2 32-bit values, we're just designing a 32-bit CPU, you need to be able to access all 64 bits of the product, right? Because otherwise, it's very common that you'll have an overflow if you multiply 2 numbers, unless you have twice the width in the product as you have in the operands. Now, the way that MIPS handled this was MIPS had a special pair of registers called high and low, which after you did a multiply, it would put the product in the high and low registers, and then you would have to follow that up by a move instruction that would copy either the high or the low to a general purpose register. So in MIPS, if you wanted to do a multiply and access all 64 bits of the result, it took 3 instructions. One was the multiply, and then the move from high, move from low. RISC-V also requires 3 instructions to perform a 64-bit multiply, but the way they handle it is a little different. There's a mul instruction which will store the lower 32 bits of the product in the destination register, and then there's a mul high instruction which will put the upper 32 bits of the product in the destination register, right? So if you want to get all 64 bits, you got to do a mul followed by a mul high on the same inputs, on the same input registers, right? Now, they also have a mul H unsigned, which is needed if you're doing an unsigned multiply, because if you multiply 2 numbers, it doesn't matter if it's signed or unsigned with regard to the lower 32 bits. But the upper 32 bits will be different depending on if it's assigned or unsigned. So be aware of that. In Lab 1, we're doing unsigned multiplies. So you're going to be using the mul HU. If you use the mul H in your Lab 1 code, it's not going to work. Okay, and then we've got kind of same kind of instructions here again. for arithmetic and shift, except the difference here is there is an immediate for the second operand. So this is for doing operations on constants. Just be aware that you might remember from MIPS that the shift instructions by default took an immediate, constant shift amount rather. And then if you wanted to use the shift amount in a register, it was a shift variable instruction. Whereas in RISC-V, they changed it to where if you want to shift by an immediate, it's SLLI. And if you want to shift by a variable, by a register, it's just shift left logical. You guys with me? Not a big deal, but I found that, at least in terms of RARS, it's kind of unforgiving with this stuff. So if you don't put that I there, you'll actually, you'll get an error. Like if you want to do a variable shift, it won't like, fix it for you, Okay. And then we have 6 branch instructions for every possible way to compare two numbers, signed and unsigned. So we have equal, well, not every possible way, I guess. We got equal, not equal, greater than or equal. Branch less than, and then there's unsigned versions greater than or equal and less than, right? Because we don't need an unsigned version of branch of equal or branch of not equal. So yeah. And then, so these are the branch instructions. So these are conditional branches that do a comparison and then change the program control flow if the comparison is, true and just is essentially a no-op. If the comparison is false, it falls through. Doesn't change any state. And then you have these unconditional jump instructions. There's a branch, which really should be jump, but they call it branch. So in MIPS, this was jump. This is the unconditional jump to a label. Then there's a jump and link that links back to the destination register. By convention, it's usually 1, but you can change that. And then jump and link register, which jumps to the address that's in a register, which is used to return. Like, so in other words, the way this is supposed to be used is you first do jump and link to a function, and then when you're ready to return, use the jump and link register to return. You jump to the whatever register you link to in the first instruction. Typically, when you do that, you also have a stack where you're storing these link addresses on a stack. I teach that in 212, but in this class, we don't typically even use a stack. Our codes are really simple. But the stack pointer is initialized in RARS, so you have the option of using it if you want. But again, to use that, you have to be able to load and store too. And we're not implementing loads and stores on our CPU. So you can implement a stack in Lab 1, but then the problem is that the goal is to use Lab 1 code as a test code for your CPU. So you should try to restrict yourself to instructions that we're going to be implementing in the CPU. You guys with me? Okay. And then I listed the load and store here, even though we're not implementing these. And then there's a load up or immediate, which you probably remember from MIPS had one of those too. It takes an immediate and puts it in the left side of a register. The only difference is that in RISC-V, the immediates are 20 bits, whereas in MIPS, they were 16 bits. And then the store, I hate this. This is one thing that really bugs me about MIPS and RISC-V. So the convention is that the destination is always first, right? But in the store, it's not true, because in a store, you're taking the contents of the first register and you're writing them into the label, which is appearing second. So in a store, the destination is second, whereas in every other instruction, it's first, right? So I was hoping they were going to fix that in RISC-V, but they didn't. They left it. They used the MIPS convention for that. Okay, any questions about that? I know I went through that fast. If you need some help remembering this stuff, feel free to ask me. And like I said, I don't want this to be an assembly language programming course. You should have had a lot of that in 212. The only reason we're going over it is I know from experience that when I didn't do that, I had a lot of students that asked for review because it's been 2 years since they took it, and you don't really use any assembly language outside of that 212. So that's why I'm doing this review. And the reason we're using assembly language at all is because you need to understand it really well in order to build a CPU, because the CPU is just a machine that executes assembly code. So you have to understand how the assembly code works. And the reason why we're doing this specific lab is because in the past, when I would assign the CPU and the test program in one lab, students would have to write them both concurrently, and then they would test it, and if it didn't work, you didn't know if it was a software problem or a hardware problem, right? So the intent here is that you're going to write this code for lab 1, and hopefully it'll be bulletproof, or at least if it's not, you'll be able to fix it because you'll get a grade on it. And then when you go to use it to test your CPU, if there's any problems, you know it's a hardware problem because the software has been validated, right? So that's why we're doing this. And so we just have the one lab in assembly. You'll have to write a little bit of extra assembly in lab 3, but it's fairly small. Okay, so what are we going to do? So the goal by the end of the course is to design a CPU and then have it do something practical, something tangible. And so the idea we came up with without having to rely too much on software is to essentially build a calculator that will take the inputs on these switches. So there's 18 switches down here, and we're going to interpret these as an 18-bit number. So an unsigned 18-bit number. So the number that you're entering on these switches is an integer between 0 and 2 to the 18th power minus 1, right? Which is 262,143, right? And then we want to calculate the square root of that number and then display it on these hex displays. But because that number is going to be a fractional number, we're going to assume that the first 3 digits are whole digits and the other 5 digits are fractional digits. You guys with me? So you have to pretend like there's a decimal point after the 3rd digit. Now you might say, why not just light it up? I mean, there's decimal points on these things. Yeah, but they didn't wire it. There's no wire between the FPGA and the decimal point. So you have to pretend, unfortunately. I don't know why they did that. They ran out of pins or what, but so does that make sense? So if you put in, for example, 2 on your switches, right, which is basically putting up switch number 1, it's going to calculate the square root of 2, which is 1.4 something, right, 1.44. And so what you'll see is 00144 and then whatever digits come after that on the displays, right? Makes sense? Now you might say, well, wait a minute, why are we restricted to integer inputs and fractional outputs? That seems dumb. Well, it's just because of restriction on the number of inputs that we have here, that's all, right? Now the problem is, though, there is some numerical things that are a little weird here. So try to, this gets a little confusing. So the hex displays, we're treating this as a fixed point number that's in base 10. What that means is that the unit in the last place, which is the least significant decimal digit, carries a significance of 10 raised to the -5th power because there's 5 fractional digits, right? So in other words, if you have a 1 on this display, that represents 1 over 100,000. That's 1/100,000th, right? That's what that would mean if you see a 1 on here. The problem is that in your code on your 32-bit processor, we're going to have to use fixed point notation on there as well, okay, except it's going to be in binary, okay? So the way that we'll do that is we're going to take the 18 bits that we bring in and we're going to put those as whole bits, right? And that leaves 14 bits left over for fractional bits. Does it make sense? Because we got 32 bits. So if we have 18 of them are the number you put in here on these 18 switches as an integer, that leaves 14 bits left over that we can use as fractional bits. Because internally, inside the program, you have to have fractional numbers if you're calculating square root, right? You got to have fractional, and we're just doing positive square root, so no imaginary. This is just the real part, no imaginary numbers here, okay? Well, what's the problem there? If you have 14 fractional bits, then the unit in the last place is going to be 2 to the -14th power. In other words, the smallest value you can store in a 32-bit number with 14 fractional bits is 2 to the -14th power, which is 1 over 16,384, right? So basically inside the hardware, your accuracy is 1/16,384th, 16,384th, right? Whereas on the hex displays, your accuracy is 1/100,000, right? So what that means is that based on this fixed point format we're using, you're going to have a little error on here, right? So this error may be off. The number you get may be off by, I think, is as much as like 5/100,000ths, right? 5. So your last digit on this hex display may be a little bit off, but it'll be as close as you can get using this numeric format, this 32-bit, 14-bit numeric format. You guys, now you might say, well, come on, there must be a solution to this somehow. Sure, yeah, you could have more, you could get more precision, but then you would have to have more than 32 bits, right? You'd have to manage larger than 32-bit numbers in your code, and that would complicate things for you guys as programmers quite a bit, at which point you wouldn't want to write that in assembly code. It would be better to do it like in C and then assemble it. You guys with me? So what I'm saying to you is that when we're grading this, we're going to be expecting that you get only within the accuracy that is expected based on the format that we're telling you to use, which is 14 fractional bits. Okay? So let me talk about that a little bit more. So fixed point is where you have integers, but you just pretend like there's a decimal point, or more accurately, a radix point, because these are binary numbers, right? I still call it a decimal point, though. So there's a decimal point somewhere in here, right? So all that means is that, for example, if this is a 6-bit number, I have to decide how many fractional bits I want to have in there. In this case, I'm going to say 3. That leaves 3 whole number bits, which means that if you look at the fractional value, right, which is 5 here, the fractional bits is 5, right? That means 5/8, because 2 to the third, I got 3 fractional bits, which means the fractional part is essentially 2 to the third is the range there, right? And so this is 5 over 2 to the third. This is just 5/8. And then the whole number part is 5. So this is 5 and 5/8, essentially is the number that's in there. Does that make sense? So the problem, though, with this is that there's no hardware support for fixed point. In other words, we're just building a fixed point arithmetic on top of integer instructions, right? And what that means is that if you multiply 2 fixed point numbers, the product is going to have a different number of fractional bits than the operands do. So what you're going to have to do is add the number of fractional bits that you had in both of your operands, and that's how many your product will have. So if you have an integer and you multiply it by a fixed point number, right, then the product will have the same number of fractional bits as the fixed point number, no problem, because the integer had 0 fractional bits, right? But if you have 2 numbers that are both in fixed point, like for example, this one has 4 fractional bits and this one has 4 fractional bits, then the result will have 8 fractional bits, right? That's just how it works, right? You might remember doing that in base 10 in grade school. But what ends up happening is that you as a programmer are then responsible for taking this product and converting it back into the original format with 4 fractional bits, right? So basically what that means is that after you do this multiply, you have to follow it up with a shift instruction that's going to shift 4 fractional bits that we gained when we multiplied, shift them out, which means that you're going to round down. So you're going to have some round off error when you do this, right? So we're going to round down, but that's okay. We're just going to assume that every one of your fixed point multiplies, assuming both operands have fractional bits, you're going to have to follow that up with a shift, right? Now, if there was hardware support for fixed point, it would do that automatically, right, in the hardware. But we don't, and in fact, RISC-V doesn't, as far as I know. Neither does MIPS. In fact, I don't know any processor except for like specialized neural processors like the Google TPU, or at least the original one before they introduced fixed point, floating point. Usually, you know, this is done in software is what I'm trying to say, right? You guys with me? Okay. Does that make sense? Okay.
I have a question about the hex display. Is it using ASCII as the input?
No, we're gonna in lab 2, we're gonna design the decoders for that in hardware. So we're not, don't worry about that yet. I was giving you the the overall goal of the class, but in this lab, we're just doing the software. So you don't have to worry about the FPGA board or the hex displays, anything yet, okay? And that's also by design, because obviously I haven't had a chance to lecture on any hardware stuff yet, so that's why we're starting with this, so we can get started right away. Okay, so I think I mentioned most of this stuff. So the range of a fixed point number is going to depend on the number of whole bits, right? So as you reduce the number of whole bits to get more fractional bits, you're losing range, right? So that's a problem with fixed point. That's why it's not used. That's why floating point is preferred, because floating point allows the decimal point to float, right? And that way you can get a huge amount of range and you can keep the same precision as the number of bits. The other problem with fixed point is that the precision is not the width of the number. So if you have a 32-bit fixed point, that doesn't mean you have 32-bit precision, because in a fixed point number, the leading zeros don't count towards your precision. You guys remember in grade school, you talk about significant digits in scientific notation. So in a fixed point number, any leading zeros in that number don't count towards your precision. The only ones that count are the ones starting with the first bit, the first 1 bit, starting from the left. So that's why I refer to the number of bits as the accuracy, and the precision is actually variable depending on what value you have in there. Whereas in floating point, because you can move the floating point decimal point around, you always get precision that matches the number of bits that you have for your mantissa, right? Does that make sense? So anyway, none of that's not really super important to the project. I just wanted to mention that. Okay, so one final thing is I mentioned this whole notion of multiplying and having a product that's twice the width of the operand. So in this lab, we want to use 14 fractional bits and 18 whole number bits. So when you multiply that together, when you multiply two values in that format, you're going to get 28 fractional bits and 32 plus 4, 36 whole bits. So the number of whole number bits grows to 36 when you multiply, and the number of fractional bits is 28. Well, 28 is almost 32, right? So it's really important that when you do that multiply, you have to keep all 64 bits. And when you shift that value 14 bits to the right to kind of round it down and get it back into the right format, that shift operation has to be performed across 2 registers, right? So normally when you shift, it's 1 instruction, but because we're doing a 64-bit shift, it's going to take 3 instructions to do it. So the way that works is that you're taking an 1814, right? You're taking, well, I should say 32-bit number with 14 fractional bits and multiplying it by itself. And you might say, wait a second, why are we doing that again? Because in the square root algorithm, we're doing the square root algorithm, which I'll talk about in a second, relies on us guessing what the square root is and then squaring it to figure out how close we are to the real answer. So what's happening here is we have a guess and we're squaring it. And when you square it, those 14 bits are going to expand to 28 fractional bits, right? And then 36 bits that are non-fractional. And then in order to convert this back into this format, the 14 fractional bits, you're going to have to shift 14 bits to the right, but it has to be done across 2 general purpose registers because we don't have 64-bit registers in here. We just have 32-bit registers, right? So, so how do you do that? Well, you take the least significant 32 bits, and you just shift that 14 bits to the right. That's pretty straightforward, right? But then the upper 32 bits, you have to shift that 18 bits to the left, right? Why? Because the lower bits on that guy have to be in the upper bits of the other guy. So in other words, we're going to take 32 bits, we're going to shift that 18 bits to the left, and then you OR them together. And what that's going to do is it's going to take the upper 18 bits from the original low register will be in the lower, the upper, I think I had a typo there. So we're shifting this 14 bits to the right. So it's the upper 18 bits from this guy, right, is going to be in the lower 18 bits. Yeah, I actually got that right. Yeah, I got that right here. The lower 18 bits of this one after we shift it. And then the upper 14 bits of the most significant register will be up here. Does that make sense? So so these 14 bits from here is going to shift to left. 18 bits of this guy are going to shift to the right, and then we're going to OR them together with a bitwise OR, right? Which will basically merge those two guys together. So what you end up with is a final result that is in the original format. So this is a little bit, this is a bit misleading here because this is 1814. So this 14 are the fractional bits, but in reality we're getting 18 bits from the original, low part of the multiply. Does that make sense? That's a little confusing, but the idea is to basically take whatever bits would have been shifted across the boundary. Like you have to think of these two registers as being next to each other. Whatever bits would have been shifted out of this upper register are supposed to be shifted into this lower register, but there's no hardware, there's no mechanism to do that. We can't do that. So the way that we can hack around that is we take whatever bits would have been shifted out of this upper register and we just put them the opposite direction. We just put them where they need to be, and then we use an OR to basically simulate the notion of bits crossing this boundary when we shift the register pair, right? So that's all you got to do in order to square the number and then readjust the decimal point back to where it needs to be. So in other words, you have to translate this into assembly code is what we're asking you to do. Okay, so for the square root, how do you do a square root? Well, one of the problems is that we don't have a divide instruction in our CPU. RISC-V has a hardware divide, but the last time I tried to implement it, the divide filled up the whole FPGA. And the reason was because I was trying to do a single cycle divide. So in our RISC processor, we're assuming that our ALU is a single cycle ALU. So all the operations are performed inside of one cycle. If you try to do a divide inside one cycle, it's pretty ugly because it has to create a huge circuit to do that, right? You can do a divide pretty efficiently if you make it a multi-cycle divide, right? So if you're willing to stall the CPU whenever a divide instruction is fetched and then give it time to chunk on it for a few cycles, that would be fine. But the problem with that would be it would complicate the control. The control inside your CPU would become very complicated, right? It's possible, but we just didn't want to have to, I think that's too advanced for this class. So as a result, we figured out that we'll just try to avoid doing a divide. If we had a divide, we could calculate the square root very efficiently using the Newton-Raphson method. The Newton-Raphson method is basically where you guess at the square root, and then you subtract the function, which in this case is x squared minus s, is the function we're trying to find the root of. You take f squared minus s being the input and x being the guess. You evaluate that and you divide it by f prime of x, the derivative, right? Which is actually just 2x in that case, right? So that's very efficient. That's the Newton method. However, because we don't have that divide, we can't divide by, we don't have a divide instruction, so we can't divide by a variable. Now we can divide by a constant using fixed point, because fixed point gives us fractional number support, and so instead of dividing by a constant, we can just multiply by 1 over the constant, right? The inverse of the constant, right? Which is what we'll do when we do our binary to base 10 conversion code in Lab 3. But unfortunately, if you have to divide by a variable, and you don't have a hardware instruction for doing that, the only other option is to create an iterative divide algorithm using shifts and subtracts, which I used to assign in 212. But I think that would be more expensive than just doing a binary search version of the square root, which is what we'll do instead. So a binary search is less efficient, but it doesn't require divide. Basically, the idea is, again, you just guess at what the result is. You square your guess, and then you compare that guess to the input value. And if your guess was too high, then the square of your guess is too high. And if your guess was too low, then the square of your guess will be too low. And all you got to do is then adjust your guess and try again, right? That's basically the idea. Now, the catch, though, is to make this efficient as possible. The amount that you adjust your guess by each time you're off, right, is going to be divided in half every single time. So, for example, if I start out with a guess of 0, and I square 0, I get 0, right? And then I'm going to compare 0 to 2, and 2, that's obviously too low, right? So I have to add to my guess. So I'm going to set my initial add amount to 2, right? But the next time I make an adjustment, the amount I adjust by will be half of 2. So it'll keep getting divided by 2. So once I add 2, now my guess is 2, and I square that and I get 4. That 4 is too high because I'm trying to get to 2, right? So I'll subtract this time, but now I'm subtracting only by 1 because I'm having to whittle away at my adjustment amount. So 2 minus 1 is 1. I square 1 is 1, too low. So I add, but this time I'm adding 0.5, so I'm at 1.5, right? Now keep in mind that the square root of 2 is like 1.4, right? So you can see how I'm getting closer. I started out at 0, and now I'm starting to converge in on the answer to the square root of 2. 1.5 squared is 2.25, a little too high. So I subtract, this time I subtract 0.25. So now I'm at 1.25, I square that, I'm at 1.5625, too low. So I add, this time I add 1/8. So now I'm at 1.375, so 1 and 3/8. I square that, I get 1.89, a little too low still. So I add, this time I add 1/16, and now I'm at 1.4375, which I square, and now I'm getting close. Now the square of this is 2.0664. Still too high though, so I subtract 1/32. Now notice that every time I make an adjustment, it's always a power of 2, right? 2, 1, 1/2, 1/4, 1/4, 1/8, 1/16, 1/32, 1/64, right? You can see what's happening here is that this step is a fixed point number that's just getting shifted by 1 bit to the left each time, right? And there's only 1 bit set in that fixed point number, which is why all of these numbers are powers of 2. They're negative powers of 2, right? At least at this point, but they're powers of 2, right? So then finally, you can see that at this point I'm at 1.4, and I just keep converging in. Now what ends up happening here is that eventually your step, as you keep shifting your step value by 1 bit to the right, eventually you'll just shift it off and it'll be 0. And that's when you know to stop, right? Once your shift amount, once this step goes to 0, that means that you've run out of precision, you've run out of bits, and then you can stop. Or if you guess the right number, if x squared equals s, right, s being, again, your input, then you need to bail out. Because if you don't bail out, the program will continue to run and you'll lose the right answer, right? If you find the right answer and you don't stop, you'll never get it back again. You'll never find that right answer again because you'll lose the ability to get to it because the step keeps going down. Make sense? So that's the algorithm for finding the square root. So the idea with the board is we're going to take 18 bits and treat them like an integer, and then find the square root. But in this lab, we don't have to do that. We can actually just provide a full 32-bit input number that's in fixed point, meaning we can have a fractional input value for this program. You guys with me? What I'm saying is that when we put this on the board, the input has to be an integer because we only have 18 switches. But when we run this in the simulator, we can just give it a 32-bit input, which allows us to put a fractional input into the board, right? And the code is the same. It won't make any difference for the code. The only difference is that in the board, you just have to add 0 fractional bits here, right, to the input, whereas in this lab 1, you don't have to do that. Make sense? But there's a catch. Because RARS, the simulator, doesn't have an unsigned function for reading an integer from the console. And if you put in a number that's big enough for the sign bit to be 1, in other words, if you type in a number more than 2.1 billion, positive 2.1 billion, RARS will say, hey, you can't, no, I can't, it'll give you an error message, and it's like, oh no. So I can't actually like put all the switches up. Like whatever the equivalent would be of putting all the switches up, RARS won't take it because that last switch is bit 31. Right, or the leftmost bit. So how do you get around that? Well, for a while, I didn't think there was a way around that. And then one of my really good grad students said, there's an obvious solution, right? You're saying that the problem is it's a signed input, but you want an unsigned number, right? just have them, if they want to put a big number in, have them convert it to the negative equivalent and put that in and treat it like a big positive number. I was like, oh, I don't know why I didn't think of that. Yeah, that's a great idea. The problem is that it gets a little complicated, and let me show you why. We can handle it, but I'm going to give you all the conversions for this. Okay, so this is the lab sheet. And by the way, it's due on September 8th, which is a Sunday. Usually they're due on Friday. But if you remember from my syllabus, I said that your late penalty only accrues on school days. So if it's due on Friday by midnight, technically you can turn it in on Sunday without any kind of penalty, right? So that's why I just make it due on Sunday. So it's just that way I don't get the question, because everyone will ask about that. Okay, so the goal is to write a RISC-V assembly language program that reads a 32-bit signed integer input value from the console, interprets it as an unsigned 32-bit number with 14 fractional bits, computes the square root, and prints the output value to the console as a 32-bit value with 14 fractional bits. Okay, so the problem here, as I mentioned, is the value conversion. So the issue is that the number you type in has to be a converted form of the number you want to actually calculate the square root of. So that's why I'm going to call input raw is the number you physically type into your program. And input actual is like the logical value that you want to actually calculate the square root of. You guys with me? So in other words, if you want to calculate the square root of the value 1, the value you actually put in there is 2 to the 14th power, which is 16,384, right? So 16,384 means 1 in this format, right? Now I know that seems needlessly complicated, but it's kind of the only way to do it, right? It's the only way to do fixed point, unfortunately, right? And then likewise, if your input value is more than 262,144, if it's greater than 131,072 rather, right? Which is 2 to the 17th power. If your input is 2 to the 17th power or higher, that means that the RARS is now confused because the sign bit is now 1, right? The most significant bit of the number you're putting in is 1. So if that happens, you have to make this adjustment where you subtract it from the complement, which is 2 to the 32nd power, and negate it, right? So to give you an idea of what I mean by this is that these are the test inputs I usually use. So if your input raw is 16,304, the input actual is 1, the square root of 1 is 1, and so your program should kick that value back. If you put 0, then the output should be 0. If you put negative 16,384, right, that actually doesn't mean you're putting a negative number in. That means that you're actually putting in an actual value of 262,143. And again, this is just because this negative number is meant to represent a larger positive number. And then, you'll get the square root, which is 511.99902, which in order to adjust this back to an output raw, you would multiply this by 16,384, right? So in other words, basically all you're having to do is shift numbers, right? In order to convert to this fixed point. Make sense? If any of you have any questions about that, or if you're confused, if you look at that, let me know. Okay. Okay, so that's the goal. The whole program is like, less than 100 instructions. But it does require you to have if statement, and you have to have a 3-way if then else, because you're checking to see if x squared is greater than the input value, if it's less than the input value, or if it's equal to the input value. So there's a 3-way condition there. And then, of course, there's a loop that loops over the squaring. The body of the loop is square it, shift it, compare it, adjust it, repeat, right? That's basically the algorithm, right? Okay, so what about RARS? So this is RARS, the simulator. It looks exactly like Mars. You might have used it in 2.12. There are a lot of web-based RISC-V simulators out there. I've tried a lot of them. None of them are as good as RARS. A lot of them don't have system calls. Some of them don't have good debugging support. And other ones are just unstable. If you want to use a web-based one instead of this Java-based one, you're more than welcome to, right? But I still recommend RARS. I still haven't found anything better on the web. Like when I say web-based, I mean like an actual web page that has a RISC simulator. It's possible. It's just I haven't found a really good one yet. RARS is a simulator and an editor, right? in order to get it, you have to download it from the Dropbox here. So you can download RARS from right here. Now, also, I recommend you download it from here instead of from GitHub, because this version of RARS has actually been modified by us because we added a coprocessor register in here used for reading data from the switches and writing data to the hex displays, right? That's the way we do I/O in this class. It's not important now. It's not relevant now, but our modified version of RARS has an extra thing that's specific to this class. Makes sense? Okay, so that's RARS. And then once you download it, you just download it in your home directory and you run it with Java, -jar RARS. Because for whatever reason, you can't just double click it in Linux. I don't know why. You can do that in Windows, assuming you have Java installed. But if you try this, look what happens. You get this. You get this error message here. Not really sure why this is happening, but you can fix it by using a different Java virtual machine than the one that's installed in Linux by default. And the way you do that is, if you go back to the, it's kind of hard to read here, but if you go back to the Dropbox, you'll notice that there's a command here that says alias java equals user bin jvm java 11 openjdk amd64/bin/java. Apparently, I don't know why this is, but there are two Javas on these machines. One of them is the open source OpenJDK, and that one runs RARS just fine. The one that comes in Ubuntu by default doesn't, because you get that error message, right? So all you got to do is stick this, if you put this command in your .bash RC, so you can just open your .bash RC and stick it in there at the end. Just paste it in there at the end, right? It'll run that when you log in, or technically when you open a shell, right? And then I already have it in there somewhere. And then once you do that, then if you type again, java-jar rars.jar, you hit that and it will come up. There it is. There you go. So that's the Linux. And this runs on Mac OS and Windows just fine. It's just Ubuntu that's being a jerk about this for some reason. So you can work on this lab on your own machine. You don't have to be in here to work on this lab. All the other labs will require you to be here. However, we're still doing groups, right? You can still work in a group of 2, right, for this. For this lab, if you want to do this lab by yourself and then form your group for lab 2, that's fine. I don't really care. This is not very difficult, but if you want to form up your groups now, that's totally fine. Okay, so that's RARS. So I'm going to use the Windows RARS. Well, it's not really Windows. I'm going to use it in Windows. So this is RARS. And so if you remember from 2.11 or 2.12, they have these directives that start with dot. So normally you put dot data to signify when the assembler should start putting anything under there in the data section, right? And dot text is when it signifies when the text or the code starts, right? If you don't have any load or store instructions, you don't actually need to do that, because if you don't put anything, it assumes that it's text. But the problem is, if I screwed up in my last lab because I took them out to make that point, and then I put some data in, I forgot to put it back in, and I had an error someone had to point out to me. So I'm just going to leave them in. So for the text segment, let's do a system call that reads a text, an input from the console, right? So in order to do that, you can just go to help rather, and look under syscalls. And they have a bunch of system calls listed. These are fairly standard, but if you want to read an integer from the console, the way this works is the read integer is system call number 5. And in order to tell the operating system that you're using system call 5, you load the value of 5 into register A7. Okay, and then and then you call the eCall function, and then when it comes back, you'll have the value the user typed in will be in A0. So let's try that. So we go over here and say load immediate A7.5, and then you just do eCall. Okay. Now you might be asking, like, well, wait a minute, you never showed the load immediate instruction. This is fake. It's actually just an add I instruction with register 0. But load immediate is a lot more readable, in my opinion, than that, right? Because it describes what you're doing as opposed to what your intent is rather than what the machine is actually doing. So I'm going to hit the assemble button here. And, oh, no, that's fine, replace. I'm going to hit the assemble. Oh, I got to save it first, sorry. Save it. And hit assemble, this little icon here. And you probably can't read this in the back, but it says add I with register 0 and eCall. And then if you want to run it, you can just hit the run button. And it's, oh, I'm sorry. Actually, well, it doesn't normally bring up that dialog. I turned something on to do that. It says enter integer value. I'm going to say 10. And then if you look over here under, if you can find A0, you can see that 10 is now in register A0, which is actually register 10, ironically, right? So it doesn't normally do that. Hold on, let me show you why it's doing that. There is an option that says pop-up dialog box for input syscalls. I have that turned on. Normally, if you hit rewind here and you run it, you would type it in down here in the console, right? The console at the bottom. And so you can see now I've got 5 in register 10, right? Okay, so now what if we want to, let's say we want to do some fixed point stuff now, right? So let's say I want to divide the number I type in by 10, right? So as I mentioned, there's no divide instruction, but I can take the reciprocal of 10, 1/10, and I can store that as a fixed point number and then multiply my input by that, and that should divide it by 10, right? So first you have to decide how many bits you want, fractional bits you want in your value of 0.1, right? So I can pick anything, arbitrary number. I'll pick 14, like we use in the assignment, right? So how do I say 0.1 in 14 fractional bits? Well, remember that 2 to the 14th power is 16,384. All I have to do is divide that number by 10 and I'll have 1/10, right? So I can load, I'm going to do this, let's see, yeah. I'm going to do a load immediate into S0. I'm going to put 1,638, which is 16,384 divided by 10, right? Now, obviously it's rounding it down. It's not exactly 0.10, but it should be close enough for us, I hope, right? So we got that in there. And then we just multiply. We do a multiply A0 by S0, and then I want to put the result into, I'll put it back into A0, right? Okay, now the problem is that once I do that multiply, I'm going to have fractional bits, so I got to get rid of those fractional bits. So I'm going to do a shift right logical immediate A0, A0, 14. And once I do that, I should now take whatever value I put in, it should be divided by 10. Let's see if it works. Oh, but I want to print it too. So how would I print? Let's print it too. So to print something, I'm going to go back to this system call, and I'm going to go to print integer, which is system call 1, and the integer is in A0, which is good for us because it's already there. So all I have to do is say load A7 with 1 and then eCall. And by the way, you might wonder what eCall stands for. I have no idea. In MIPS, it's syscall. They changed it to eCall in RISC-V, which is, I don't know what that means. So that seems like kind of an asinine change. But okay, so we're good to go, and let's try it. So it assembled, run it. So I'm going to put in a big value. Now here's the problem though, okay? Any value I type in that's going to overflow when I multiply it by 1,638 is going to bug the code out, right? I got to make sure I don't overflow. I'm kind of limited in what I can put in. So I'm going to try a big number, but it's probably not going to work. So I'm going to try 76,543, and I'm going to do that, and Well, it kind of worked, but not exactly. I got 7652. It's kind of weird. I didn't actually expect that to work. I thought it was going to overflow. Let me put a bigger number in. So rewind. Oh, let me put a smaller number. Let's put 123. There you go, 12. I don't know if you can. I know in the back you guys probably can't see it, but trust me, it says 12, right? So that worked, right? If I put 1, 2, 3, 4 in, 1, 2, 3, oh, okay, 1,232, I get 1,100 or 123, so that's good, right? If I put in 1, 2, 3, 4, 5, 6, okay, that's screwed up, 1, 2, 3, 4, 2. So I think that's because it overflowed. If I try 1, 2, 3, 4, 5, 6, 7, 8, well, now it's just garbage, right? I just get a garbage value. I mean, 185,000, it makes no sense because it overflowed. Now, I could fix this if I did the trick where I, extracted all 64 bits of the product and only shifted, shifted across the two registers, but I'm going to leave that part up to you guys, right? But how about, what if I want to make a loop now, though, and divide it by 10 multiple times through a loop? So if I want to do that, I can come back here and set up a little for loop that's a post-test for loop. So I'm going to set up inside of this. I'm going to initialize a register S1. See, this is where I'm going to run into trouble because I got to now I got to pick registers. I'm going to initialize S1 to 0. That'll be my loop counter. And then I'm going to put my loop label, not there. I don't need to do that every time. I'm going to put my loop label on the multiply. And I'm going to move this down just so this initialization is closer to the loop body. You guys with me? So I'm setting I to 0, and I set up a label here for the loop. And then I'm going to multiply, shift, and then set the system call and eCall, right? So that should do it. And then pretty much I want to say branch less than, or no, I have to add 1 to my loop counter, right? So add I, S1, S1, 1, and then branch less than, if S1 is less than, well, how many times am I going to do this? I need another, see, I hate this. I have to set another register for my loop count, how many loops I want to go through. I'll set that to S2. I'll make it 5. I'll do this 5 times. So now I have to compare this to S5 and then go to my loop, right? So S5 is my loop limit, how many times I want to loop. S1 is this counter. It's initialized to 0 here, right? Now notice this is a post-test loop, so technically you can't call this a for loop, but for all practical purposes, a for loop, right? It's just that it's going to go into this loop always at least once, right? So you be aware of that. But I'm okay with that because I know I want to do it 5 times. Okay? Now, the problem is, I think, I'm going to assemble this and run it. I type in 3, 4, 5, 6, 7. Okay, so you'll notice that 3, 4, 5. I mean, it's kind of, the problem is that it doesn't print new lines out when you print a character, print a number. So I got to do new lines here. So I'm going to go back in the code and I have to print a string. And this is why I have a data section, by the way. So I have to define a label here called new line, and I'll make it a string with the \n, new line character. And I'm going to have to basically print this in between printing the numbers. So after I print the number here, I have to do another load immediate into S7, and I have to do the print string function, which is print string, come on, I'm running out of time here. Print string is 4, right? And A0 is the address of the string. So I'm going to put 4 in there, and then I'm going to load address SA0 to new line, right? So that new line is just a symbol, that has an address in memory. The load address is going to put that in there. And then I'm going to basically use to print that. The problem is that, I don't know if you guys caught this, but see, I made the same mistake here I made earlier, where A0 is my value that's being carried from one iteration of the loop to the next, because A0 is the number that keeps getting divided by 10. it's also the value that I'm using to print, right? So I need to figure out a way to solve this because my A0 is getting wiped out here. So you can fix it pretty easily by just, before you do that, I can move, I guess I just use A1. I'll move A0 to A1, and then I'll do the E call here, and then I'll move it back, right? So pretty much I'm going to load, I'm going to set up system call 4, which is print string. I'm going to save A0 into A1. I'm going to take the address of new line and put it into A0, which is the carriage return character, or the new line character. Then I'm going to e-call that, and then I'm going to restore the original A0 here, right?
Move is not that's the assembler.
Yeah, it's actually, yeah, it uses an add-I. It uses add-I again. It's a pseudo instruction. Okay, so, and it's actually not move, it's a copy, technically. I don't know. That's also annoys me about assembly. They always have move, but it's not really a move, it's a copy. Okay, so I'm going to run that, and then I'm going to put 3, 4, 5, 6. Okay, so now it's scrolled. I'm going to hit this little button here that'll, okay. So 3, 4, 5, 6, 3, 4, 5. It did not, okay, something's wrong. It was supposed to do that 5 times, so I got a bug in there somewhere. So you had to do another system call to get it a new line instead of writing on the top. Yeah. Well, no. So there's 2 system calls here. There's one to print the character, right? So I'm going to put these together. So there's one to print the character here, and then there's another one here to print the new line. And then I am saving the character that I printed. I didn't use A1 for anything else, did I? No. And actually, that wouldn't matter because I think it was S1 is the issue here. So I initialize that. Oh, S5 is, oh, that's the problem. Where's S5? Oh, no. Oh, S2. Oh, that's the problem. Yeah, I see it. Okay. Yeah. So the loop counter was supposed to go to S. The loop limit was in S2, but I assigned it to 5, and then I got confused and put S5 here. That should be S2. So that's the problem. You see that? I got my wires crossed there. Okay, so let's back up, run. I'm going to type in, let me expand this before I do that. So I'll type in 5, 6, 7, 8, 9. And so, yeah, 5, 6, 7, 8, 9. Okay, this 5, 6, 7, 7. So I think it's rounding here. So I think the problem here is that, notice how it's supposed to be 5, 6, 7, 8, right? But because I did that shift, right, I shifted the result, it rounded down, and so I ended up 5. It should have rounded it potentially up to 8, which is where it should be. But then 5, 6, 7, so that knocks off the 7, 5, 6, 5, 0. So it works after that. So we did have a round off error there. Now let's see if we can fix that. If I go over here and I add more fractional bits, I might be able to fix that. So I'm going to hit the down arrow here. So if I go over here, if I want to change the number of fractional bits, all I have to do is change that the shift amount, which is 14. If I want to have, say, 18 fractional, I'm sorry, I need more. Yeah, I need more fractional bits, right? So I'm going to make this 18 here, right? And then my 0.1 is no longer 1638. Now it has to be 2 raised to the 18th divided by 10, right? Which is going to be 2 raised to the 18th is 262, 144. So it's going to be 26, 214. 26, 214. Okay, so that's my 0.1, and now I've got everything into 18 format here. So run and expand, and I'll put the same test, 5, 6, 7, 8, 9. Yep, there it is. Cool. Check it out. Now it works. 5, 6, 7, 8, 9, 5, 6, 7, 8, 5, 6, 7, 5, 6, 5, right? So it's peeling off a digit each time through, and it's doing it through using a fixed point multiply as opposed to a divide, which is normally how you do that, right? But again, it's because we're dividing by a constant. If you're dividing by a variable, then unfortunately there's no trick to that one. Okay, any questions? Well, that worked out perfectly. That's everything I had. So the assignment is on Dropbox. If you have any questions, let me know. It's due on September 8th.